Hi and welcome back. Let's start this video by recalling some of the most important results about symmetric matrices. We called the square matrix symmetric if it is equal to its own transpose. Then we saw that the symmetric matrix only has real eigenvalues, and if it has two different eigenvalues, then the corresponding eigenvectors are orthogonal. In this video, we will expand on the second result and what it tells us about the diagonalization of symmetric matrices. For this purpose, we quickly recap what we know about diagonalizability. An n times n matrix A is called diagonalizable if it can be written as P D P inverse, with D a diagonal matrix. If A is diagonalizable, then the columns of P are linearly independent eigenvectors of A, and the diagonal entries of D are the eigenvalues of A in the same order. In order to understand the diagonalization process for symmetric matrices, let's first assume that we already know that the symmetric matrix A is diagonalizable. Then, for each eigenspace we can find an orthonormal basis of eigenvectors, using the Gram-Schmidt procedure if necessary. These bases together form an orthonormal basis of Rn, since we know that eigenvectors corresponding to different eigenvalues are orthogonal for symmetric matrices. In particular, if we let P be the matrix which has these eigenvectors as columns, and D the diagonal matrix with the corresponding eigenvalues on the main diagonal, then we can write the symmetric matrix A as P D P inverse, where P has orthonormal columns. You might recall that we encountered matrices with orthonormal columns before. Indeed, a square matrix P is orthogonal if its inverse is equal to its transpose. This is precisely the case when P has orthonormal columns. So we just saw that a diagonalizable symmetric matrix could be diagonalized using an orthogonal transformation matrix P. This special property leads to the following definition. We call matrix A orthogonally diagonalizable if there exists an orthogonal matrix P and a diagonal matrix D such that A is equal to P D P inverse. Since the matrix P is orthogonal, this means that A is also equal to P D P transpose. In other words, A needs to be diagonalizable with an orthogonal transformation matrix. As always, the columns of P are the eigenvectors and the entries on the main diagonal of D are the corresponding eigenvalues. If you like to think about diagonalization as a change of basis, this means that for an orthogonally diagonalizable matrix, you can simply rotate space in order to transform the matrix into a diagonal matrix. In particular, we can conclude from our previous considerations that any matrix that is both symmetric and diagonalizable is also orthogonally diagonalizable. Indeed, reflection and projection matrices, which we considered previously as typical examples of symmetric matrices, can easily be seen to be orthogonally diagonalizable. The subspace W through which we reflect or on which we project is the eigenspace corresponding to the eigenvalue 1, while the orthogonal complement of the subspace W is the eigenspace for the eigenvalue -1 for reflections or 0 for projections. In both cases, the eigenspaces are clearly mutually orthogonal. In addition, it is well known that the dimensions of W and its orthogonal complement add to the dimension of the full space. This means that we can indeed form an eigenvector basis, so both of these types of matrices are orthogonally diagonalizable. As a more concrete example, consider the orthogonal projection onto the subspace W spanned by the vector 2, -1. The corresponding matrix can be seen to have the eigenvalues 1 and 0. The corresponding normalized eigenvectors are 2 over square root of 5 minus 1 over square root of 5 and 1 over square root of 5 to square root of 5. Indeed, these eigenvectors form an orthonormal set. So we find that the orthogonal projection can be orthogonally diagonalized using the orthonormal eigenvectors as the columns of the transformation matrix. and by using the diagonal matrix with eigenvalues 1 and 0 on the main diagonal. So now you might wonder which matrices, apart from the symmetric ones, are orthogonally diagonalizable. It turns out that symmetric matrices are the only type of matrix that is orthogonally diagonalizable. In order to show this, we let A be any orthogonally diagonalizable matrix, and we write A as P D P inverse, where P is orthogonal and D is diagonal. Then we can work out the transpose of A and see that it is equal to A, where we use that P is orthogonal. So that means that A is symmetric. We conclude that for diagonalizable matrices, being symmetric and being orthogonally diagonalizable is equivalent. So the next question would be, is every symmetric matrix diagonalizable? Note that in general it is very hard to determine whether a matrix is diagonalizable, as we need to have a basis of eigenvectors for the entire space. Luckily, it turns out that symmetric matrices are in fact always diagonalizable. We will not prove this result here. The preceding considerations lead to the following powerful theorem, which is known as the spectral theorem for symmetric matrices. It states that the matrix A is symmetric if and only if A is orthogonally diagonalizable. So if we want to construct this orthogonal diagonalization for a given symmetric matrix A, we should follow the following algorithm. First, we should compute the eigenvalues of the matrix. Then, for each eigenvalue, we should construct an orthonormal basis for the eigenspace, using the Gram-Schmidt process if necessary. Here, it is important to make sure the eigenvectors are normalized. Then, we can construct the orthogonal matrix P by using the normalized eigenvectors from step 2 as columns. Finally, we construct D by placing the corresponding eigenvalues on the main diagonal. As an example, consider the following symmetric matrix. Using the characteristic equation, we find that the eigenvalues of this matrix are 125 and 45, with multiplicities 2 and 1 respectively. The corresponding eigenvectors can be computed as usual. Here the eigenvectors corresponding to different eigenvalues are orthogonal, but the two eigenvectors for lambda equals 125 are not orthogonal. So we should use the Gram-Schmidt process and normalize them in order to make them orthonormal. The matrix P now has these eigenvectors as columns, and D is the diagonal matrix with the eigenvalues on the main diagonal. You can check for yourself that P is indeed an orthogonal matrix. For the final part of this video, consider a symmetric matrix A with orthogonal diagonalization given by A is PDP inverse. We let V1 up to Vn be the columns of P, which are then the orthonormal eigenvectors of the matrix A, with corresponding eigenvalues lambda 1 up to lambda n. Then, since P is orthogonal, we can write A as the product of the matrix with the lambda I Vi's as the columns, with the matrix with the Vi's as rows. Using the so-called row column expansion, we can write A as the sum of expressions of the form lambda I Vi transpose. This representation is called the spectral decomposition of A, as it decomposes A into parts determined by the spectrum of A, which is the set of eigenvalues of A. Note that every column of, for instance, lambda 1 V1 transpose is a multiple of V1, so such a matrix has rank 1. In fact, V1 transpose is the matrix that corresponds to the orthogonal projection onto the subspace spanned by V1. Let's conclude this video by considering an example. We let R be the reflection through the subspace spanned by the vector 2 minus 1. Since R is a reflection, it has eigenvalues 1 and minus 1, and we can compute the corresponding orthonormal eigenvectors V1 and V2. Note that V1 is on the line through the vector u, and V2 is orthogonal to u. This allows us to write down the spectral decomposition of R. Note that the first matrix in this decomposition is the orthogonal projection onto the subspace W, while the second matrix is the orthogonal projection onto the orthogonal complement of W. This means that if we want to compute the reflection of a vector through this subspace, we can first decompose this vector into a part in the direction of the vector u and a part orthogonal to u, and then let the reflection act on these separate parts. In addition, the spectral decomposition has various practical uses in data analysis. We will not delve into this right now, but we will come back to these applications when we consider the so-called singular value decomposition, which can be seen as the generalization of the spectral decomposition for matrices that are not symmetric. That's it for now. Make sure to practice these concepts and see you next time.